Okay, not Cy. So from here, okay, we are going to look at deflection. Okay, so we're going to apply again the same deflection is equal to PL over AE. Right? We're still going to apply the same thing. And then the notation is positive. It's going to be in tensile. Negative is going to be what? Compression. Okay, so D is at the top, the support. So this is still the support. The support is still there. Okay, we did not remove the support. Okay, so deflection of 0.1 or section 1. So section 1 is going to see what? It's going to see both the 150 and the what? The 200. Okay, so it's going to see the minus. So the 150 is going to be what? Compression, yes or no? Right? 150 is pushing into compression, and then the 200 is going to induce a what? A tensile, right? So the analysis is based on what? Tension and compression. Nothing to do with going up is positive, coming down is what? Negative. Or going towards the left is negative, going to the right is positive. Are we clear? Because this analysis is based on what? Deformation. Okay, it's not a static analysis. Static analysis, then you say left is negative, right is positive, up is positive, down is what? Negative. For this case, in terms of deformation, compression is negative, tension is what? Positive. Remember that. Okay, a lot of students are making mistake at this case. Okay. Are you considering dimensions of brass and steel in 3 sections? Yep. So 1, 2, 3. Okay. So deflection. So number 1. So it's going to see the minus 150 times 10 to the power 3. Then it's going to see the 200, because 200 is going to induce the what? A tension. Right? So the 150 is pushing into 1. The 200 is pulling away from 1. Right? At section 1, so it's going to induce tension. Then you divide, so the length. So the length is what? I'm lost for the length. The length is equal to 0.25. Right? The A is the bigger area that we calculated earlier. So the area that we have calculated is what? The area is 1.9635. 1.9635. 1.9635 times 10 to the power 3. And then this is made of brass. So I did mention that brass is equal to what? 101 times 10 to the power 9. Okay. So this will be equal to, so 50 power 3 times 1.25 divided by 1.9635 power 3 divided by, oh, minus 3, sorry. I missed up. Okay, so minus 150 plus by 200 power 3 times by minus 150 power 3 plus by 200 power 3 times by 0.25 divided by 1.9635 power minus 3 divided by 101 power 9. So it's equal to 63.0. So positive 63.032 or 0315 times 10 to the power minus 6 meters. Okay. Then section 2. Section 2 will not feel the 150, but will feel the tensile of what? 200. Okay, so 200 times 10 to the power 3, right? Multiply by the length. So the length over here is 0.5. Divide. So this is the cross-sectional area is different now. So it's still 314.159. So it's 314.159 times 10 to the power minus 6 divided by 200 times 10 to the power 9. Right? So this is going by what? This is going to a mode of tension. So 200 power 3 times 0.5 divided by 314.159 power minus 6 divided by 200 power 9. So it's equal to 159 or 1.59 1.5916 times 10 to the power minus 3 meters, right? And then finally, the deflection at section 3. So section 3 is not going to see anything at all, right? So it's equal to 0. I'll write this out for you guys. Multiply by 0.25, divide by 1.9635 times 10 to the power minus 3, and then multiply by 101. Why 101 is made of brass? So this will be equal to 0 meters. Okay. So from here, we are going to calculate the deflection due to the load. Okay. So sorry, this is also positive. Okay. So that is also going positive. So you have 63 positive, 63.0315 times 10 to the power minus 6, and then you plus by 1.5916 times 10 to the power minus 3. So this will be equal to 63.0315 power minus 6 plus by 1.5916 power minus 3. So it's equal to 1.654. So I get 1.655. Okay, 1.655 times 10 to the power minus 3 meters. Okay, so this is due to the actual load. Okay, so the next case, the next one, okay, so I'm going to do, yeah, I can do left and right. So step number 2. Anyone, any questions so far? Anyone? I hope you are like me, okay? When you do this in vertical, when you put the beam vertically, you see better rather than horizontally. Horizontal, you might get, you know, I'm not sure, you might get lost. Okay. And then so step number 2, right? Step number 2, like before. Okay, step number 2 is we are going to place a redundant load at point C. Okay, so we're going to put a redundant load at point C now. Okay, so I'm going to copy the same thing. I'm going to put over here. Okay. So what's going to happen now is we are not going to consider what? We are going to ignore the 500, no, 150. We're going to get rid of this arrow. We can get rid of the 200. All right. Now we are going to place, right? We're going to place a load over here, right? In that direction known as RC. Okay, the redundant load at point C. So you know that RC, okay, so this is redundant load. Like before, RC is going to induce a compression in section 1, section 2, and section what? 3. Okay. So over here, then we're going to write what? Deflection due to the redundant load is equal, so section 1 is equal to what? Section 1, so it's equal to minus RC, redundant load at C, RC multiplied by the length. The length over here is 0.25. Divide by area. So area, we have our area is equal to what? 1.963 times 10 to the power minus 3. Divide by Young's modulus, which is your 101 times 10 to the power 9. Okay. Then again, you minus RC again. And this is for section number 2. And it's again going to induce compression with a length of 0.5. Then divide by the area is 314.159. And now this time it is what? It is 200 because it's made of what? Steel. and then again minus by the same thing because you have, okay, so I'm going to minus again. I can put twice, but I'm not going to do that. Okay, so this is for section 1, section 2, and this is for section 3. My apologies. Okay, I think it's confusing for you guys. So this all over here, in fact, all these are pluses, right? All these are plus. And why is it minus? Because the RC is going to induce a what? It's going to induce a compression. I'd rather do this so you get less confusing. Okay, so you get less confusing at this stage. The last thing I need you guys to be now is being confused. Okay, and it's my fault. I apologize. So delta R is equal to 0.25 divided by 1.963 pound minus 3 divided by 101 pound 9. So it's equal to minus 126.1. Okay, it's equal to minus 126.1. 1.261 times 10 to the power minus 9. And this is your RC. And then minus by 0.5 divided by 314.159 pound minus 6 by 200 pound 9 is equal to 7.958 times 10 to the power minus 9 RC. And then minus again, so it's the same thing, 261 times 10 to the power minus 9 RC. So this will add up to be 1.261 pound minus 9 times 2 minus by 7.958 pound minus 9. So it's equal to 10.48, right? So I get 10.48 times 10 to the power minus 9 RC. Okay, so that is your RC. So from here, we are going to apply, we're going to apply, right? Delta L plus by delta R, the whole thing will be equal to 0. So delta L is 1.655, right? 1.655 times 10 to the power minus 3. And delta R is equal to minus 10.48 times 10 to the power minus 9 RC. Okay, so RC is equal to 1.655. Okay, 1.655 times 10 to the power minus 3. And then we're going to divide by 10.48 times 10 to the power minus 9. So your RC is equal to 157. Okay, 157.920. Okay, well, 157.920 times 10 to the power 3 Newton, and it's going upwards. Okay, so you have calculate your RC already. So you calculate the reaction force at point C. So over here, where we construct our free body diagram, right? RC, all right, what we have done is we assume it the wrong direction, right? Because RC is going to induce a what? The redundant load will be in compression. Okay, so now you just don't wipe out, just cancel, okay, and say this is the actual. As engineers, you don't wipe out, you don't take a wipe, you just wipe out because that is your initial assumption, but you know that it's wrong. So now it's equal to 157.92. Okay, 157.92 times 10 to the power 3 Newton. Okay, so you can also calculate the reaction at dx. Okay, so you want to calculate the reaction at point D. So we're going to calculate the reaction, or we can calculate dx. Okay, so you apply static analysis. right? So summation about forces in the x direction is equal to 0. So you have minus